This is the second of a three-part demonstration of how to debug a Scala service with a slow actor leak. The first part was how to set up networking and connect to the remote resource using a SOCKS proxy. The second part is just a brief view of using VisualVM. The third part is using a heap dump to work upwards to find the leaked resource and identify the fix to the actor Scala code. So let's get started. So the JSTAT daemon that's running remotely on AE8 automatically is populating the Netty server associated with the PID 16671, which we go back over to that HTOP or rewind back to where I showed it. That would be the process of the JVM that we're going to debug. If there were more than one, we'd actually see more than one here if they're owned by Einstein.
So JSTAT just connects to all JVM?
It's kind of a JMX proxy. So if I double click it, it'll connect up to that. Gives us an overview, the process ID, the host, the main class, the version of the JVM. It turns out that as part of what we did, Andy and I up-leveled the stack so that Einstein now is running JDK 1.8. It's the first of our services to run JDK 1.8 on top of Ubuntu 16.04, the most recent Ubuntu release. So here you can kind of look at stuff like system properties. You can actually kind of introspect a bunch of stuff. I've turned on and I've installed a bunch of plugins. There's a whole bunch of available plugins. I've installed almost every single one of them. We've got the most relevant ones are Visual GC, being able to look at introspect beans, mbeans, the ability to, take a look at garbage collector stuff. So those you install locally, and then you connect them up to your remote end. Monitor is one of the most important things we want to use. This will actually, since the time of connection, start monitoring CPU, the classes loaded, the number of daemons, threads, the total number of threads, or I guess the peak and the live peak. Here is where you would actually take a heap dump. We'll come back to that in a little bit because that's for offline analysis, which was really what we wanted to do. You can take a look at threads. I'll let people play with all this stuff on your own, but just as a very quick view, here you can see the ones that are running, their various states, how much time they're taking, what percentage. If we sort by percent, and there's some that are running at 100%. Oh, that's total. Okay. The sampler starts to get interesting. Now these, because we're on JDK 1.8, we have both memory and CPU. If you have a 1.7, you can still use this with 1.7 JVMs. It's just that only the CPU will be available for sampling. It's normally stopped. You turn it on, you start sampling CPU. Turn on memory, you start sampling memory. It's a sampled profiling tool. So as it starts to gather, you'll see, in this case, the update period is 3 seconds. And you start to see the accumulated time. You say that 38%, 41% here is in the fork join pool scan. This shows you what threads are doing, and you can monitor them over time. You can take snapshots. You go look at thread CPU times. So you can dig into the performance behavior of your process, and you can actually create quite a bit of intuition about what's going on, how it's architected, whether there's bottlenecks. Very useful. Great to contemplate offline. Here it's currently not doing much, so I could actually coordinate over here with, say, the log. That's my VisualVM. You connect back up to it. I use tmux to keep sessions active, so if you disconnect from the VPN, you can still use them. So this is a tail -f on the log. In this case, it's in the, if we see what is it, it's actually tail minus f on etc service Einstein process 9001 log main current. That's the this is launched with runit. So we could be looking at these logs and switching back and forth to the VisualVM and see when something comes along. I see it's not ready to progress. It gets a trigger, but hasn't actually fired up the computation in this particular. There, now it did. So here we start to see threads that take CPU doing something more. Just finished, so we may have missed it. But you can take a look at memory. In this case, this shows you, and this was the particular analysis we were doing for finding the leak.
And we clearly do not see those problems that we were seeing before. The data points being up there, right?
We do not.
That's a difference.
Now we're going to take a heap dump and bring it back and look at it. So
see the contrast.
Right, and the heap dump, of course, will let us look across everything. We'll open an old one and we'll see the difference between the two. This is actually useful. I haven't done a heap dump since we did the upgrade of the entire stack.
Okay.
So this will be a live verification of the fix that we made. Okay, so this shows you what's being allocated. The vast majority of it is just strings, character arrays. Colon colon is the, Lisp, it's the const cell for lists in Scala. Scala has generic lists that are strung together with the small object that has the head and the tail. So this is the small list object, and that's the second most numerous after strings. This is the string storage, and then string object, big decimal object, tuples, blah, blah, blah. It goes down from there. I'm going to finish the vertical or the horizontal look at things. mbeans is very useful. We actually added, maybe I'll actually hit that. From here you can introspect things that publish beans. So we can open up and take a look. There's Java Lang, the mbean server delegate. There's a lot of machinery here that we don't really care about. The kind of things we do care about are the garbage collector. It turns out there's two of them. This particular Einstein process is configured to have both concurrent mark sweep and par new. So within that,
Did we configure it on the command line? Did we make those choices actually?
I believe so. We'd have to go back and look at the launch. I think it's launched with arguments,
That
or
require both.
it's either in a properties file or it's on the command line. But there is a configuration for Java, the JVM, to use both. Within it, there's things you can get. If we look at the memory manager, let's see. Here we go, CMS old gen. This was the thing we cared about, is the size. There it is, right. There's Eden space. If we actually go back to the Visual GC, we can see old gen information. I'm doing this just diverting here a little bit. We can see a lot of statistics calculated on the garbage collectors. In this case, we see the Eden space where new objects are born. Survivors are kept and they're moved out of Eden into one of these shorter term queues, and then if they become mature, they go into the old gen, and there's a flow through these different pools of memory, and different garbage collectors have different metrics. And the G1GC, for example, has many different Edens that it works with, and they're particular to the the garbage collector in question. One of the things we did was we used this introspection on the beans to configure the JMX trans so we could actually look at Stackdriver and plot for Einstein this old gen number. So the stats here are interesting to look at live. Over a long period of time, you can look at those we touched on mbeans, buffer pools. I haven't bothered with this. Console plugins, they're whatever. I'm not worried about that. Tracer, there's some interesting things you could do here with tracing, but we're not going to cover that today. So we go back to the sampler. You can force a GC if you want, which is interesting. We can do that from here too, I think. No. So go back here, we'll perform a GC. You'll notice that actually the monitor should see the heap go way down. Right now is at 8 gigabytes. You notice it went boom, way down when we perform the GC.
Wow, that's a lot of cleanup.
Yeah. So it got rid of, 8 gigabytes worth of trash. When you do a heap dump, it turns out that that implies doing a GC in addition. So it'll perform another one, but I don't really care all that much.
So the GC precedes the heap dump, correct? Because it
Yes.
wants to see what is left right after doing the heap dump.
Yes. A heap dump would go into /temp, which is a small file system. I need to put it in the mount file system, so I happen to know that that's a place where I can put this heap dump. So it created it. If we go back to our instance over here, there was already one there. If we look at one was created today, June 1, there it is. It has a date stamp in it. You'll notice it's mode 600, which is a good idea for things like heap dumps. But let's chmod 644 on the heap dump so I can copy it back to my local machine. Okay. So let me disconnect from the remote machine. We're going to look at. Now I have wrote a little script called fetch dumps.sh right now. It just rsyncs it into all the hprofs into a directory. There's only one in there right now. When I do a fetch dumps.sh, it's going to rsync it back. Okay, now it copied it. We can go back to our VisualVM. And in here, we can shut down this if we don't want to have load on the Einstein instance that's there. So we can shut it down. Let's see, is it still? Yeah, it's all fresh now, so I threw away the context. I shouldn't have done that. But now we can open our heap dump. So we do that by opening heap dumps. I created a symlink for hprof in my home dir down to where I'm actually storing these things because it's tedious to get down to it. We grab the heap dump that is the most current one that we just opened or just created. And from the heap dump, we see the summary information about it, the threads at the time of the heap dump. Heap dump is a snapshot. It does a garbage collection, and what's left is recorded into this hprof file. So this is the end of part 2. Continue on to part 3 to see the use of the heap dump in debugging the actor system.